of experiment, DOE, and we are going to go and see what do we have in subchapter 6.1, which is the analysis of variance. We can have an ANOVA here, okay? Analysis of variance. Normally people will call it as ANOVA, and you also can see the slide that I've shared last week. So currently we have 32 students. Okay, speaker saya okay tak ada masalah Saya punya mikrofon semua dengar Okay. Saya akan terangkan sedikit demi sedikit. Saya harap kamu boleh faham. Sekarang ada 38 student. I think another 3 or 4 students left. Okay. We go to subchapter 6.2, which is the analysis of variance. We call it as ANOVA. And I think I'll start my presentation. I want to show you the slides on my screen. Okay, so this is in our statistics, introducing the ANOVA in our statistics. It's just started 1 year before. There are 3 or 2 semesters. Okay, students already introduced to this ANOVA. So ANOVA is a model. Actually, it is a model that we use to design an experiment so that we can whether the factors in our experiments give significant effects on the results or not. So the general equation is shown in this equation 6.5, whereby we have in the equations the symbol there. It includes the value of the overall means, the i's level means, okay, and for the tau I, it means the i's level effects, and we have epsilon ij, which is the random error. So the formula look like complicated, but once you go through to this slide one by one and understand it, I think you will realize that the calculation is not complicated at all. But when you want to solve a problem using ANOVA, the works that you have to do to get the conclusions is a bit long, because you have to calculate a lot of value here. So it just need require you to do calculation carefully, not doing any mistakes, so that you can have a correct answer and correct conclusions at the end of your analysis. So this in page 27, I think the pages number in the slide that I gave you is a little bit different compared to this slide today, because I have deleted some of the pages. So this is the first example of data in experiment or in analysis that we use to explain what is ANOVA. So this table showing the results of process capability on two type of machines. Okay, process output. Okay, and the machines types is the input. So in statistics, we call this machines type or the input, we call it as factors. So we have two factors, and then we make sampling. We do the measurement. We have done 3 trials for each factors. So from this table, you can now can see that it have one factors, which is the machine, but it have two level. Sorry, it one factors, which is and we have two level, which is USA and Japan. So this factor is from the category of non-numeric factor. Okay, so we have 3 responses for each for each level. And for USA process capability, you have 2.1, 2.0, and 1.9. For Japan, we have 0.9, 1.0, and 1.1. So number of observations, you can just count it here in the table. You have 6, or maybe you can calculate it. Just A times N, you will get the alphabet N. You have the total number of observation, which is 6 in this example. So this is the basics knowledge, or basics the foundations that you have to know about the designs of experiments. And then the calculations, you have to do it so that you can do further calculation on the tau, on the mu, the y bar, and so on. So at the previous slides, these are the equations that we given for solving the ANOVA model, and from the table you can arrange it as this. The first column here is y1, y2. Second column, additional second column, is y bar 1 and y bar 2. So, and we have the mu1, mu2, and tau 1 and tau 2. So the formula as given before in the previous slides, we have y1 is 2.1 plus 2.0 plus 1.9. We have a 6. Okay, whereby y1 is the accumulated value of results from one level, and y bar is the mean value, whereby you divide 6 by 2 and by 3, you get 2. So you get 2. So this value, you put it substitute it in all of these boxes. So for y1 you have a 6.0, y bar 1 you have the average value which is 2.0, and mu2 is 2. So mu1, the calculations is mu1 is considered equal to y1 bar. Okay, so then we have tau 1. The tau 1 is mu1 minus mu. So you can have mu1 which is 2, no, which is 2 minus 1.5. Okay, so 1.5 is actually formula approximately y1 bar minus y bar dot dot. So you have 2 minus 1.5, we have 0.5. So tau 2 also you can calculate it using the same formula, you will get minus 0.5. So we have to put it as minus or plus. So at the end, you will be able to fill up all of the boxes in these tables. And in this case, y double dot here you have 9.0, which is the accumulations of 6 and 3. And then the y bar dot is 9.0 divided by 6. Whereby this 6 here is the total of the responses. You have 1.5. Okay, and then you have mu. Mu, you can assume it equal to y bar double dot, which is 1.5. So this step here is very important. So make sure you don't do mistake on calculation. Calculating the values in all of these boxes in the table. So from there, the next evaluation is you have to do evaluation on the errors. So for instance, if I is 1, j is 1, yij is equal to y11. Y11 so is 2.1. Okay. So the formula here, E11 epsilon 11 is equal to y11 minus mu1. Epsilon 12 is equal to y12 minus mu1. Okay, so and so on, the rest using the same concept. So you have this set of table format. So actually this table here is showing the actual formula. This is the results that we are going to calculate, and this is the final result that we can get when we calculate the results in this table. So from here, y okay, y11, where do we get the y11? Maybe some of you don't understand where do we get this y11. So y11 is this one. Y11, y12 is 2.0, y13 is 1.9, y21 is 0.9, y22 is 1.0, y23 is 1.1. Okay, that's what it's mean by y11. Okay, so in this case you have a 1, y11, y12, y13, 121, 122, and 123. So actually this value here is the error between the mean and all of the value in table 8 here. So next, after you got it, if you want to know what is the actual tau value or the differences between each responses, so maybe you can plot a graph. This graph is showing the value of y11, which is 1 to 1, compare to the others data in the same level. Okay, so this is also showing if in this case the tau is quite balanced, whereby the mean is in the middle and you have the error at the upper side and the bottom side. So it is in a balance error. Okay, just want to show that. And the other one here is showing that the tau, some of the results is in the plus value, but only one of the results is minus value. Okay, in minus direction. So in this case is one of the result is in plus direction while the others in the minus direction. So the value of tau there here is showing the magnitude of the influence. Okay, this how does these factors give influence to the data. So another things that we need to do in analysis of the ANOVA using the ANOVA is the hypothesis test. Hypothesis test is to test if a factor has effect on the responses. So if the factor has no effect on the responses, the response is always the same regardless the change of the factors. So we have calculated the value of tau, tau1, tau2, and so on. If you have three factors, three level, okay, that means you will have three different tau value. But if the factors doesn't have significant effect on the responses, or the tau value will be small, but and if the factor does not have any effect on the responses, the calculated tau will be 0 or near to 0. Okay, if the factor has effect, the tau will be non-zero, will be not equal to 0, and it will be near to 1 as the effect is getting larger or getting more significant. So the value of tau will be near to 1. So as you learned in a previous chapter, you have learned about the null hypothesis and alternative hypothesis. So we have to explain, or we have to express the problems that we want to analyze by using a mathematical method, which is we use the symbol of HO, H1. Okay, HO, tau1 is equal to tau2 is equal tau, and so on, is equal to 0. Or alternative hypothesis stating that tau, all the tau is not equal to 0. Okay, so the larger the value of any tau, the more effective the factor will be. So there are also different types of error here in analysis. Whether we want to reject the HO or whether we want to accept the null hypothesis. Okay, so from here, let's see, we have another machining example. Okay, so we have another data here. We have the process capability, CP. We have 1.6, 1.5, and 1.4. We have for Japan 1.4, 1.5, and 1.6. We still have one factor, and then we have two levels. And then each factor we have three responses. So total of the response is 6. So using the previous formula, you may calculate it again using the same method in the previous slides. So you can calculate it. You will have mu1 is 1.5, mu2 is 1.5, mu is 1.5. So the T1 is equal to mu1 minus mu, it's equal 1.5 minus 1.5 is equal to 0. So when the tau 1 for this, for USA is 0, tau 2 for the Japan is also 0. That means in this case, the machines has no effect on the process capability. So this is the conclusion that we can get if the data from the experiment is presented in this or in such values. Okay, so when we plot the graph, maybe we'll have like this. Mu is 1.5, and then we have a little bit larger, a little bit smaller, and then it's a very symmetrical data. And when we calculate the tau is equal to 0. That means the machine has no influence. So minor variation is caused by errors rather than the machines. So the next slide showing the steps that we have to take, we have to follow in conducting the analysis of variance. So the first one, we have to calculate the sum of square. We have to determine the degree of freedom. We have to calculate the mean square. We have to calculate the test ratio F0, and then we can make conclusions. So in this chapter, in analysis of variance, we are going to use table 9 in statistics book. So I have already uploaded the PDF file for F table. Okay, F distribution table. Maybe you can see it in another file or another soft copy of the books. You can refer to table number 9. Okay, so this page showing the formula that you can use to calculate the sum of square. But let's see, just see directly to the next formula here, whereby it's explaining more detail on how we are going to calculate the SST, SSF, and SSE. So the first one is for SST. The second one is for the SSF. You just look on this red rectangular box mark area, so you can see the formula that we can use it easily for the calculations of SST, SSF, and SSE. So the next slide here showing what does it mean by SST and SSF. Okay, SST, it is a measure of total variability in the data, whereby the SSF is the sum of square of differences between factor level, averages, and grand average. So it means the SSF is the difference between level. Okay, and SSE, square of differences between observation and their level averages. So it also compare between different differences within the levels. So important things that you have to remember is SST must be equal to the accumulation value of SSF and SSE. So next we have the alternative formula for calculating the sum of square. We call it alternative. But in the next examples, we are using this formula to calculate the sum of square. So you can refer back to the process capability value. So in this case, we take this sample of data, which is we still have two levels for one factors, and each level have three responses. Total of the responses is 6. So we have A is the level, N is the responses, and we can calculate the value of Y dot, Y1 dot, Y2 dot, and Y dot dot, and also the rest. So these calculations is actually you can refer to the previous slides. In my slide, it's page 28, but I think in your slide maybe 29 page, in page 29. So you can calculate it again. Use this method. Produce a table like this. Okay, like is shown in this slide, and then you can uh, resume. Okay, you can go further calculation on the using the next method, which is explained in this box here, the SST, SSF, and SSE. So you can calculate the SST, which is the square of the first data plus the square of second data plus the third data, and then go to the next level data, square it, each of it, accumulate all of them, and then we deduct it or minus with 9 square divided by 6. So 9 square, 9 is the value of y dot dot, and we can get 1.54. So the next one is you can calculate the SSF. In this case, we have 1.5. The SSE is 0.04. So what does it mean by the value of SST, SSF, and SSE? So how do we use it? Look on the next slide. It's stated there, if the SSF is large, it is due to differences among the means at the different factor level. Okay, the mean at different factor level. So a large SSF means that the tau I, okay, is great. If the SSF is large, then we can say that the tau is bigger. Okay, it's big. It is an indication that the factor has significant effect on the response. So if the SSF is large, that means the factor has significant effect. And the SSF usually is standardized by taking the SSF divided by SSC. So by comparing the SSF to SSC, we can see how much variability is due to the changing factor level and how much is due to the error. So in this case, when we have a condition here, we conduct the analysis on two examples. Let's see that SSF we have a SSF divided by SSE, we have a 57.5. So does it effective or not? So we can say that the factors is effective. But when we have it 0, so we can say that the factors is not effective. So the next one is calculation whereby we involve the number of the degree of freedom, DOF. Okay. Total number of observation as shown in the previous slide, the beginning of the subchapter 6.2, the large but n here is equal to small a times n, small n, and the degree of freedom SST is as in equation 6.14. So we have the rest formula degree of freedom for the SSF and SSE. So this formula here, we can rearrange it in the next formula equation for of the OF, whereby AN minus 1 is equal to A minus 1 plus A times N minus 1. So we can take back the example from the previous slides. We still are looking on the process capability of machines from USA and Japan. Okay, when you calculate the degree of freedom using the formula given in this slide, previous slide, so you will have value of N. Large N here is 6, SST is 5, SSF is 1, SSE is 4, and then you can have it like this, whereby 1 plus 4 is equal to 5. So it will prove, okay, it will give show that this equation here is correct. So to calculate the mean square, okay, the mean square, the ratio between a sum of square and its DOF, okay, MSF is SSF divided by A minus 1, MSE is SSE divided by A times N minus 1. So we have to calculate the MS for the SST. So from the value of this MSF, MSA, we can use it to calculate the value of F0. Okay? So from the value of F0 here, we can do judgment by using table F distribution table that I uploaded in the Google Classroom. So we can judge the null hypothesis and the alternative hypothesis. If H null is true, so F follows a theoretical F distribution which is completely determined by two parameters, V1 and V2. So V1 and V2 is degree of freedom. So V1 is A minus 1, V2 is A times N minus 1. So let's see that if we have 3 responses for level 1, that means the V1 is 2. So we have 3 here. So no, the level is 2. Okay, level is 2. 2 minus 1 is 1 for V1. V1 for V2 is level is 2 times response is 3. Okay, for each level we have only 3 responses, so that means this one is 2 times 2 equal to 4 here. So from this you can refer to the table getting the value of f alpha v1 v2. So then you can make comparison on the f value. So this is a conclusion can be made in your analysis. Q is a constant, f0 as f SSF divided by SSE, and then you can have the value. So if the f0 is equivalent to SSF divided by SSE, so the standardized SSF except for a constant Q. So what does it mean by the f0 is explained in this page, whereby if the f0 is large, it means that the tau square is large. When the tau is large, the factor has significant effect on the response. Okay. Using the control limits f alpha v1 and v2, so we can look on the table. Usually the value of alpha is referred to 1% or 5%. If the problem doesn't mention any of this value, you can just assume it as 5%. So usually the analysis in ANOVA we use 1% or 5%. So F0 is calculated using this formula. F0 is equal to MSF divided by MSE. If the F0 is smaller than the value taken from the table, we conclude that the factor has no effect. And if the f0 is larger than the value that we can get from the table, we can make conclusions that the factor has significant effect. So this table, so okay, before that, the p-value, we have value here, p-value. P-value actually is the area of the curve, okay, under the line after the f0 v1 v2 value in x exists. Okay, if the p is small, it means that f0 is small, is large, then the factor has significant effect on the responses. So this next slide is showing the example of how do we read the table, but we can see also the actual table. I think I don't know. I think Dr. Hasrina already explained to you how to read the F table. So in case of you miss that one, I explained to you how to read this table. So table 9, actually in the books, statistic books produced by Murdoch. Okay. So just look on table 9. We have here F alpha B1, B2. Okay. So alpha, as mentioned before, is we can take it as 1% and 5%. Okay. So this value here is 0 0.05, 0 0.025, 0 0.01, and so on. So we have 1, 2, 3, 4, 5 values. Okay, 5 values. So when you look at the table in the bottom here, this horizontal value is for the V1, the vertical is for the V2, and the first value of each column here, each line and column here is for the value of alpha 0.05 if it is in the first part here. The second is for the 0.025 alpha and so on. Okay, so in this case, if we want to get the value of alpha 0.05 to 1, that means 0.05 will come at the first line. 0.01 to 1 means that 2 here and 1 here. Okay, we can get value of 199.5. Okay, 199.5 is the value is f alpha 0.05, v1 is 1, v2 is 4. That means we have to look on this one for the v1, we look on the v2, 4, then we have this area. But look back on the alpha, what is the value of the alpha? So in this case, the alpha we want to look at is 0.05, which is 5%. That means the value here is 7.71. So that's the how do we reach table 9. So from this calculations, you can rearrange all of the value in the table as shown in this slide, which is table 13. So if we do it, so we will have table like this. We have the F0 is 150, and if we look on the F alpha is V1, V2 is F0.05, comma 1, comma 4 is 7.71. Okay, so from this value we can see that the F0 is larger than the F in the table. So it means that the machines have significant effect on the process capability. So the next is when we have result like this, whereby the F0 is 0, and we look on the F 0.05, 1, 4 is equal to 7.71. In this case, the value of F0 that we calculated is smaller than the F value that we can get from the table. It means that the uh, factor doesn't have effect on the process capability or on the output. So this is another example showing results whereby in this case we have one vector which is the hardwood concentration, and there are 1, 2, 3, 4 levels, and we have 1, 2, 3, 4, 5, 6 responses for each level. So total up, we have 4 times 6 responses, which is 24 responses. So you can accumulate it. We have this value, we have the average, and you can use this example 3 here to do the analysis using the ANOVA. So you can calculate the SST, SSF, and SSE, and then arrange it in this type of table. So in your calculation, maybe in your final exam, the questions using the question taken from the ANOVA chapter here, from the design of experiment, when you have that kind of questions, you must create a table like this. So make sure that you create a table like this, complete it, and then you have your conclusion at the bottom of the table. That is the method how you can get full mark in these questions. So in this case, if you calculate it, you have 19.61 for the F0, and from the table you have a 4.94. That means the F0 is larger than the F table. So it means that hardwood concentration has significant effect. So this is the method that we use to judge the data. In the case of we are having one factor and we have a different level. So the next two slides here is the summary of the ANOVA. One is to decide the factor to be investigated. We have to know the levels number. We need to know the replicants, which is the response number of each level, and we have to carry out the experiment. Okay, it is recommended for you to conduct experiment in random manner. Okay, in random manner, which means that you don't have to follow the table. You have to jump from one level to different level. Okay, or if you have two factors, you can jump from different factors to different factors in random. So check if the residual is, which is the estimates of error, satisfy the requirement. Calculate the sum of square, and then you calculate the degree of freedom, calculate the mean square, calculate the F0, and you can then you have to compare it with the value from the table. If you design your own experiment, you might choose the alpha 0.05, and then from the value you have, you can make conclusion whether the factor have a significant effect on the response. If you have two different factors, you can have two different F distribution values, and then you can see which one have the most significant effect. Or maybe you can compare by using the value of tau in the previous method. So you can use the value FO, you can use the value of tau to do the evaluation in your experiment, to judge whether your data taken is applicable to draw some conclusions, or maybe you want to know whether the factors or the parameters for the experiment is effective or not before you go further on next stage of the experiment. So you can use this method. You can calculate the tau you can calculate the F. So from this explanation today, you should understand, you need to understand that we have to do some calculations to evaluate the level of significance of the factors in our experiment. So we can use method whereby we can calculate the tau, okay, and also at the same time maybe you can also calculate using the hypothesis test, which is using the F value. We calculate the sum of square, and then we can go to the value of we can have the sum of square value, the ratio of sum of square, such in this example here, okay? Or then you can also go to the calculation F0, but final calculations, complete calculations, usually we are going to see the F0, such as in this slide here. Okay. So I think that's all for today. I would like to ask you to fully understand the method I just explained today from page maybe 27 or 28. Yeah, from 26. The analysis of variance until summary here. Okay, until summary. Please make sure you understand it and you can do the calculation, and also you can create tables to showing the final results before we go to the next multiple comparison techniques in this chapter, which is the last subchapter in this course. Okay. So in your final, chapter 5 and chapter 6 will be the question that you cannot ignore. You must answer it. And for chapter 1, 2, 3, and 4 will be the elective question. You can select which one or which two of them you want to answer. So make sure you can do calculation on how to get the F0 value in this chapter.